of an introductory class in electricity and magnetism. And in this lecture, I'm going to show some examples of using Gauss's law for the electric field. There's a single learning outcome for this lecture video. It's got two parts, but it sort of makes sense. It goes along with the title. It's to learn how to use Gauss's law as well as symmetry considerations when it's relevant to determine the magnitude and direction of the electric field, as well as to determine the net electric charge in regions of space. So the way this lecture will start is an example that'll feel kind of random, but it sort of shows the power or some aspect of the power of Gauss's law. Going to do two examples of using Gauss's law to make some decisions that's kind of related to these 2 points up here in the learning outcome. In the first case, we're going to sort of willy-nilly randomly sprinkle some charge around in three-dimensional space, or at least we're going to imagine doing such a thing. So it's going to feel kind of random. And these charges that we sprinkle throughout the space can be little point charges, or they can be interesting groupings of charge. So you'll see that. And then the second example will be an example of thinking about conductors. So like, for example, a metal object, where the metal object has holes in its interior. Not on its surface, but within. So these are referred to as cavities. So for example, if you held a conductor with a cavity in your hand and you rotated this object around, you wouldn't be able to see the cavities because the cavities are covered up by the outer surface of the conductor. So the idea is in a conductor with a cavity, there are inner surfaces of the conductor. Yeah, and inside those cavities, you could say it's a vacuum or some air or something like that, or some water, or like an insulator. After this kind of like seemingly kind of random exploration of charge distributions and conductors, we're going to think about particular shapes. In particular, they're going to be symmetric shapes of charge distribution. So this sprinkling is kind of like indicating a randomness to the shape. But when we have symmetric charge distributions, the idea is we have a kind of a nice pattern. So we're going to make some decisions about the field line diagram, the electric field line diagram, based on symmetry, and that's going to indicate for us particular choices of shape of Gaussian surface. So some examples that have quite a lot of symmetry are pretty special and maybe sometimes kind of impossible, honestly, like realistically impossible. So the first one is realistically impossible. Imagine an infinitely long line of uniform charge density. So this object itself would require a space that's infinitely large. And if you think about it, if we have charge that's the same everywhere along the line and the line is infinitely long, we're talking about an infinite amount of electric charge along this thing. A more realistic example, which is interesting to study, is the shell of charge. And you should keep in mind that early on we talked about, so this is, I don't know, lecture 3 or 4 or something like that, something called the shell theorem. And this is going to essentially give us the shell theorem without actually doing any integrals. We're going to purely use symmetry arguments. So this is kind of a cool use of Gauss's law. And while, you know what, I wish that this is actually kind of a subtopic inside of the symmetry arguments. So really these two things go together. So this is the issue of using Gauss's law or thinking with Gauss's law in cases where we have very high symmetry. So very high symmetry, honestly, is not something that I'm equipped to define. But these two cases have what's, in quotes, called very high symmetry. And Gauss's law is particularly interesting in these cases, but it's because of these 2 points. Um, yeah, so lots to talk about. Here is a charge distribution, which is built out of a charge in the center, which we'll take to be positive. And in terms of this common value of charge, capital Q, we'll have 3 capital Q's worth of charge right here in the middle. Over on the right side is negative Q, and over on the left side is another negative Q. So the net charge of this configuration, or this charge distribution, overall is 3Q minus Q minus Q equals Q. So it's plus Q's worth of charge in the total. So that's the net charge of this system of charges. The field line diagram is not for any particular charge. The field line diagram is actually for the net field. So what's depicted is the net electric field throughout this space. And Gauss's law is about this net electric field. So Gauss's law says that if we pick a surface S, a closed surface S, and we think about the flux of this net electric field through our chosen surface S, all we ever get is the enclosed charge, so enclosed charge inside of our chosen surface S, divided by permittivity of free space. So this is the statement of Gauss's law. So let's pick some surfaces. I'm going to choose 3 different surfaces. So one surface is this one. So this is a surface that encloses all of the charges. So it encloses all of the net charge. We'll call this S1. And then another surface to choose that might be interesting is this one here. So let's choose it so it does something like this here. So here's another surface. Call this one S2. And let's choose another surface. How about this one? Here's a surface that encloses 3Q and minus Q on the right hand side, and we can call this one S3. So Gauss's law for S1, we imagine doing the integral over the surface S1 of how the electric field pokes through the surface. So here it is clearly poking through the surface. The field line pokes outwards here. The field line also pokes outwards here, and also outwards here, and also outwards here, because you can see this field line is making it out. So we have these 4 outbound field lines, and we can say that the net electric field fluxes out of S1, and outward flux is positive, so greater than 0. For S2, here's S2. S2 is interesting because if you look at it, can you see that here are 1, 2, 3, 4 field lines that pierce through the surface S2, but they all do it inwards, right? So there is inwards flux into S2. But then if I follow the field lines that flux, here is an out, and here is an in, and here is another inwards, and this one is outwards, right? So this is the flux line leaving the surface, but then it turns around and comes right back in. If you sort of count the piercing in and piercing out, I've got 1, 2, 3, 4, 5, 6 inwards, and only 1, 2 outwards. E net fluxes into S2 more than outwards. And this kind of a flux adds up to be smaller than 0. That's a negative net flux. And then for S3 is interesting. It's a little bit harder to keep track, but I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outwards fluxes, lots of outwards flux, and only 1, 2 inwards flux field lines. So E net fluxes out of S3 more than inwards. And so this flux is positive. So the flux is positive for S3. So we could, so the flux of the net electric field through S1 is positive here. The flux by the net electric field out of S2 is actually negative for S2, and for S3 it's, in a sense, it's more positive than what came out of S1. And if we think about it a bit, this is supposed to, oh, whoops, no, that's right. So S1 fluxes out, and Q enclosed is equal to Q net in the case of S1. S1 encloses the negative Q, the other negative Q, and the positive 3Q. So Q enclosed is Q in this case. In this case, Q enclosed is minus Q, because if you look at S2, S2 is the surface, and the enclosed charge is only the negative Q here. So I have a flux that's negative and a Q enclosed that's negative. In this case, I have a flux that's positive. I have more outbound arrows than inbound arrows, and the or enclosed charge is positive. And then down here, Q enclosed is, so S3 includes positive 3Q and negative Q. So this is positive 2Q, like this. And I've got a positive flux. So the sign of the flux and the sign of the net of the charge enclosed, they match each other, is the idea. Yeah, so this is just thinking about a distribution of charge with Gauss's law, in terms of keeping track of whether or not the flux is mostly out or mostly in, and matching it with the sign of the charge. Use I'm going to abbreviate Gauss, so just as capital G, because he is one of the ultimate capital G's in physics. So use Gauss's law to explore conductors. And in particular, this is conductors with cavities. So this is sort of like the cavity you can get in a tooth. A cavity in a tooth is a place where the tooth has worn away, and so you have, you don't have tooth there. You instead have gross stuff or empty space, honestly. So let's imagine a conductor. Right? So here is an arbitrary conductor. And the idea is inside of here is a cavity, right? So this little empty place on the inside of the conductor, the idea is like you have the conductor in your hand, and as you rotate it around, you can't see the hole because the hole is inside of the conductor. The only way that you can see the hole is to imagine taking out a saw and cutting it open, and you open it up and you can see that there's a hole inside. That's the cavity, right? So this is the little cavity on the inside. So let me imagine actually doing that cut. So here is the arbitrary conductor, maybe from a different point of view, and the hole is right here. All right, so this, it does look like an avocado, kind of, but it's not meant to depict avocado. So this right here is so-called the bulk of the conductor, right? This is the material of the conductor. But this right here is an empty, that is, it could be vacuum, it could be air, it could be any insulator, really, right? Let's say that it starts off as empty. So it's just vacuum, for example, doesn't really matter. Okay, so this is the material, right? This is all metal, and then that's a little hole or an empty cavity. And this is what this thing looks like if you saw through it and remove half of it, and so we can see the hole. Okay, so let's think about this conductor. So here's an interesting thing we can do. Let us put inside of here a little charge. So let's put a point charge, for example, Q, inside the cavity somewhere. Okay, so if we do this, there's going to be that little charge. So I'm going to update our picture. So here is our conductor, and here is the little cavity, and here is a charge. And let's imagine that this charge is actually less than 0, right? So this charge is less than 0, which means that it's a little negative charge. And so let's imagine actually this conductor has no net charge. So it's got the same number of protons as it does electrons. But somewhere down in the middle of the cavity is a single point charge that happens to be negative. So what does Gauss's law say? Well, before we check Gauss's law, we have to remember something very interesting about conductors. Remember, in the bulk of a conductor, comma, the electric field is always, so I'll put it in caps with an underline, the electric field is always 0. So in the bulk of the conductor, which is throughout this material here, if I check here, the electric field is guaranteed to be 0. No matter what charges are out here, and no matter what charge is inside the cavity, in the bulk of the conductor, the electric field is always 0. So how about here? The electric field is also 0 right there. How about there? The electric field is 0. It's just 0 everywhere in the bulk. But what about here? If I go and ask there, I am not in the bulk of the conductor. I'm actually in the bulk of an insulator instead, or an empty place. And the electric field there is definitely not always 0. How about out here? The electric field in general actually is not 0 there either. So the electric field is not 0. It's not guaranteed to be 0 in anything except for the material of a conductor. In the material or the bulk of a conductor, the electric field is always 0. You should always feel guaranteed by this. And the reason's kind of funny, but it is the reason, is because if it wasn't 0, then conduction charge would move until it was 0. If you think about it, right? If there is non-zero electric field in here, then that means that the conduction charge in the bulk of the conductor, which is free to move, is going to move under the influence of a non-zero electric field. And the way that charge will move is in the way that causes the net electric field in the bulk to become 0. And it happens very quickly. And so the reason that we say it's always 0 is because if it's not, it quickly becomes 0, just by virtue of the fact that there are free conduction electrons. Okay, so this is true. So let me go and imagine, it's hard to tell probably, but this is a black ink pen. I'm going to draw a Gaussian surface around, and this is my surface S. And think about the charge enclosed in S. So it turns out that Gauss's law says that the charge enclosed in S, actually let me solve for the charge enclosed in S. It's equal to the flux times epsilon naught. Right? If you go look at Gauss's law, this is the flux of net electric field through the surface S, where that's S right there. It encloses the cavity. So yeah, multiply by epsilon naught. And this is epsilon naught times the integral over the closed surface S of E dot dA, where these are the small area elements that show me how to get out of S, no matter where I'm at on S, and that's the electric field at the location that I'm talking about, the area element. So here, these are electric field values on S, but because S is in the bulk of the conductor, right? S everywhere on S is actually inside of conductor. This electric field, so since S is entirely in conductor, this implies that E equals to 0 everywhere on the surface S that I chose, this arbitrary surface. The only thing that's not arbitrary about it is no matter what its shape is, it completely encloses the cavity. So, all right, so what this implies
is that if E is everywhere 0 on S, then as I do this integral, no matter what the shape of S is, E is 0 everywhere, so that the flux calculates to 0. So if the flux calculates to 0, then what I'm guaranteed, because of Gauss's law, is that the charge enclosed in S absolutely is 0. And so what we can conclude is that what must happen is a charge shows up here at the boundary, right, at the surface, the inner surface of the cavity. There is a charge that shows up that's the opposite sign to the charge that's enclosed inside the cavity, right, the point charge in there. And this surface charge equals to the opposite of the point charge there. So this is absolutely true. So the charge that shows up there distributes itself on the surface in the way that it needs to, such that there is no electric field in the bulk of the conductor. But what's interesting is that if charge shows up here on the inner surface of this conductor, and the conductor as a whole has no net charge, then that means that if I have, say, 1, 2, 3, 4, 5, 6, 7 plus charges here, they must have come from the outer surface of the conductor. So 1, 2, 3, 4, 5, 6, 7. So the idea is whatever charge shows up at the inner surface, it came from the outer surface, so the outer surface is now negatively charged. And if you look at this for a second, this is pretty cool. Because of this negative charge, the field inside goes from pluses to minuses, like this. The field in between the outer surface and the inner surface of the conductor needs to be 0. And the way that it's 0 is because the field lines that point from plus to minus here are canceled by the field line that's inbound to the inner charge, so that the net field in the bulk of the conductor adds up to 0, like we know that it has to. But then on the outside of this conductor is electric field that's inbound, because negative charges, field lines go into negative charges. So on the outside of this conductor, we know that the field lines have to be inbound. And if you want to play some more games with Gauss's law, you could imagine trying out a different surface S and thinking about a surface S that encloses the entirety of the conductor, and talking about the net charge enclosed by this larger surface. The net charge enclosed by the larger surface is simple. The conductor has no net charge, even though it's got an interesting charge distribution. Its net charge is 0, but enclosed in this surface is also the original capital Q. So the charge enclosed is there, and that negative charge has a negative overall flux. And yeah, that's how you would do that kind of work. So the next example is an infinitely long, extremely thin piece of material that carries a uniform linear charge density called lambda. So it's useful, or at least easy, to think of lambda being positive. That is, this long line of charge is a long line of positive charges. So, okay, so this is the point of view in a coordinate system such that the z direction is the direction in which the line exists, and then the x and the y are so-called transverse directions. They're perpendicular to the direction of the line of charge. So I've drawn an alternate point of view with the same coordinate system, so the coordinate system's oriented the same way. where this long line of charge is represented by the dot because it's in and out of the page like this. And these are the transverse directions, x and y. So you can see that these two pictures are pictures of the same thing, but from different points of view. So in this picture, it's sort of plainly obvious, but because the charge that sort of seems to be along the origin of all the xy planes along the z-axis, because it's positive, if you put a test charge, say here, then it's going to feel a force this way on it, right, away from the positive charge down at the center. So this field line needs to look like this. And of course, the opposite side's got to look the same. And if you check in these directions, you'll discover the same. And if you check here, you'll discover the same. And here, and here, and here. So we begin to see at least a planar description of the electric field of the line charge in the xy plane. But the thing is this line charge exists for all the infinite number of values for z. So let's think about it a bit. Let's check here. Let's put a point charge here. It's some distance out the y-axis, but at a negative z. And let's say it's actually in the zy plane. What we find is if I imagine a point charge q here and ignore all of the line for negative z values or more negative z values, only consider all the positive charge above, then I'll begin to guess that I must have some electric field that points this way, right? Or at least a force on this positive charge that points this way from the upper half. But from the lower half, because that charge also exists, it also puts a force on this thing. And because the lower half is as much charge distributed the same way that the upper half is, then all I get is another equivalent but sort of another force vector, and they amount to, right, let's do parallelogram rule for adding two vectors. This right here is the force acting on Q by the entirety of the line charge, right? This is the force by the lower half, and this is the force by the upper half. And these are all vectors, of course. So, so this indicates that, at least for a point charge here, it should feel an outward electric field, right? The electric field on this side is outward that direction. And on the other side, it looks exactly the same. So what we imagine drawing is electric field lines that point directly away because I have the same amount of charge above as I do below. Distributed actually the same way because of the uniformity of the charge distribution. So this location actually in the z direction, it's not special. If I check here, I'll learn that the field lines need to point away. And if I check here, I'll learn that the field lines need to point away. That is, it seems like the field can't point in a different direction for any positive z value versus any negative z value. And what this speaks to is sort of a symmetry of the field lines. That is, we're discovering that the electric field does not have a dependence on the z coordinate. That is, anytime we check the electric field, we'll never ever have to know where we're at along the z-axis. But in the xy plane, so xy coordinates, independent of the z direction, we do need to know about x and y, because I know that a point charge far out is going to experience a weak electric field versus the same point charge when it's further in. It's going to experience a stronger electric field over here. And that is because of, you see the field lines? The field lines are wider apart, further away. So the density of the field lines is going down as we go larger and larger radius. So this is indicating that this electric field is going to have a magnitude that only depends on the combination, actually, of x squared plus y squared. That it doesn't depend on x independently or y independently. It actually depends on r, right? Which is the radial distance away from the line charge. It's not the radial distance from the origin. It's the radial distance just independent of z, is another way to say it. So this is all suggesting what's referred to as a cylindrical symmetry to the field. And in particular, it's a cylindrical symmetry for the field line diagram. And what you want to learn is that if you discover a symmetry of the field line diagram, you can carry this symmetry over to choosing a Gaussian surface S. And in this case, we'll choose cylinder surfaces, but not just that. These cylinder surfaces will share, so cylinder surfaces that share the axis with the charge, right? So they're going to be centered around the charge. So we're going to imagine cylinders drawn this way here, or this way over here. So they'll share the axis with the charge, but will not need to be located at any particular z. So what this means is I don't have any reason to think in terms of a z-coordinate. So the Gaussian surface can actually be anywhere in the z direction, and not even just that, but it can be as long as we want or as short as we want in the z direction. So our Gaussian surface is going to, for example, have to look like something like this. So this is an example of choosing a Gaussian surface. When we choose that Gaussian surface, because of the strong and the weak sort of nature of the electric field, as we get further and further out here, the field is weaker and weaker. We get to think also about having the freedom to choose the radius of our Gaussian surface. So we have a lot of freedom about choosing the height of this Gaussian surface. We have a lot of freedom about choosing the radius, but we're going to find that the choice of radius matters because further out in radius we have weaker field. We're not going to find that the up-down choices along the z-axis, they're not going to matter. But what is absolutely dictated to us by the field line diagram symmetry is that this surface, this Gaussian surface, won't be useful to us unless the Gaussian surface shares the same axis that the field line diagram has. It'll turn out that, for example, a Gaussian surface like this, it may be, it may absolutely be a cylinder, right? A circular cylinder. But if it's off the axis, do you see that the axis of the cylinder is not shared with the axis of the charge distribution or the axis of the field line diagram? So over here it's this z-directed point of view, and here it is off-axis. This dot is the axis of the cylinder. If it's out there, it's not that Gauss's law is not true out here. Gauss's law is always, always true. Arbitrary surface, arbitrary location, arbitrary charge distribution. Gauss's law is a statement about the net electric field associated with all of that stuff. So Gauss's law is always true, but whether or not it's useful if you choose a good Gaussian surface. And choosing a good Gaussian surface is based on thinking about the symmetry of the field line diagram. All right, so let's see what we can get from this. Let me redraw the situation. I don't think I need the coordinate system again. So here is this long charge distribution, lambda. And so let's, so S. So this is the surface S, the Gaussian surface. So we'll say it is a cylinder, coaxial, right? That means it shares axis or has coaxis. So coaxial with the charge distribution. And we'll say that it has radius r. So let me draw it. So here is a cylinder. It's a circular cylinder like this. Oops, actually should go across. And its radius is r. So something that nothing dictated to us, so no symmetry dictates this to us, we'll choose length of the cylinder, right? That's another aspect of this cylinder, to be L. So let me choose capital L like this. So choose length L. So it's length L from top to bottom. So must be closed, right? This is kind of a big deal. Often people forget to think about the end caps, right? Especially in like a cylinder situation. So we must also actually consider the fact that in order to close this surface, we have to consider the caps. So don't forget the caps. So here's the caps. So it must be closed. So there are two caps. And these caps are disks of radius r, right? So the area of the caps is super easy to write down. So let's go and write down Gauss's law. So Gauss's law is the integral over the closed surface S of the electric field due to the charge distribution. That is, this is the electric field due to all of the charge, everywhere, all at the same time, dotted with small area elements that tell me about the surface S. And it's equal to the charge enclosed inside of the surface divided by epsilon naught. So let's think about Q enclosed. Q enclosed, it's actually only the charge enclosed from here to here. This is the charge that's enclosed inside our surface. This up here is not part of it, and this below it is not part of it either. It's only there. And that length is L. And so if I have a charge density lambda and a length L, then this is the amount of charge enclosed in the surface. So this thing right here we can update the right-hand side of Gauss's law, the charge side, is just lambda L over epsilon 0. So, but what about the integral part, right? So this is the flux part on this side. So this is the flux through our chosen surface S, where S is described here. So this part, let's go and think a little bit. So I have 2 points of view. I have the point of view along the axis, and our Gaussian surface, which I've been drawing in black over here, which is unfortunate. So let me draw the Gaussian surface. This is the Gaussian surface here, this blue thing, or that's a cross-section of it. So, but here it is on from the side, right? So I'd like you to notice something. At the cap, right, at the top of the cap, if you look at the electric field everywhere over the surface of the top of the cap, the electric field is along that surface. The electric field does not have value 0, but what it does do is it goes along the surface everywhere on the cap. But on the top cap, and the same is true on the bottom cap, right? So if I imagine the bottom cap, which is this lower disk, the field lines are only along the cap, including the field lines heading out and into the page, right? So those are all along the cap. But on the side of the cylinder, right, which is the wrapping, in the wrapping, the electric field actually pierces the surface, and it pierces it perpendicularly. Can you see that? So the idea is this. Let's take the surface S and imagine it as the side plus the top plus the bottom. And what I just showed you is that the electric field is always going to be perpendicular to area elements of the top, and the electric field is going to be perpendicular to area elements of the bottom. But the electric field is only ever going to be parallel to area elements of the side. So when I imagine doing this integral of E dot dA over the surface S, right, you know that, like, for example, when you do one-dimensional integrals, like say x1 to x middle, some function of x dx, right, plus integral from x middle up to x2 of f of x dx. So same function, I'll go half the interval and then I'll finish with the second half. This is the integral from x1 to x2 of f of x dx, right? You know that you can do this sort of piecewise integration. You can do the same thing in multiple dimensions. So this is the full flux, but it's actually equal to a flux through the top plus a flux through the bottom plus a flux through the side. And it turns out that when I go over the top, I'll be doing area elements over the top, right? Plus the integral of the electric field over the bottom with appropriate boundaries to range over the bottom, plus the integral over the side with some appropriate integration method to take me a range over the side. Because the dot product between perpendicular vectors is 0, the flux through the top is 0. Likewise, the flux through the bottom is 0. It's not because the electric field is 0. It's not because the electric field is 0. In fact, the electric field is absolutely not 0. but the flux is 0. And Gauss's law is about the flux, not the field necessarily. Over here, though, this is not 0 in general, the flux through the side. So we are only left over with this. That is, the flux through the surface S is equal to the flux only through the side in this cylinder case. Right? In this particular cylinder case. So we have that as an update, you could probably follow this. Here is the charge enclosed over epsilon naught. It's equal to now just the flux through the side. So this is the integral over parameters that take us only over the side of the cylinder. And so those are area elements on the side. So if I go and I look at this drawing, do you remember that we had a reason to judge, and it is a judgment by symmetry, actually, that the electric field is only radially dependent. But it's not the full vector value of the electric field. It's actually the magnitude of the electric field that's dependent only on R. So if I look at this thing right here, and I remember that on the side, the electric field is only ever parallel. So check this out. This means that the dot product between parallel vectors is strictly the product of magnitudes. Right? So E dot dA in general equals E magnitude dA magnitude cosine of angle between them. But parallel implies that the angle between them is 0, and the cosine of 0 is 1. So, oops, I just said all that, but here's, so in the parallel case, the angle is 0, and this is the meaning of the dot product, or one way to think about the dot product. So the cosine of 0, this is 1 in the case of parallel, right? And so that's why I can do this, and again, I am only left over with the flux over the side. There. Okay, so now the argument becomes E magnitude only depends on R, and the surface along the side is a surface of constant R, which means that this integral, the flux along the side, is only, right, it's magnitude of E times dA over the side. So as we walk around the side and do this work, what we're always going to find is, since E only depends on R, and the side is a constant R surface, then E can come out, and what's left over is an integral of the magnitude of small area elements over the side only. And so this is the area of the side times the magnitude of the electric field that is only radial dependent. So this is at R. And the area of the side, right, if you think about a cylinder, a right circular cylinder, and this is the side, right, of radius, actually, let me not draw it up there. So I've got this axis, and it comes out the bottom, and that's the back end. And the side, if it's L tall and R wide, or in radius, So it's the circumference, 2 pi r. That's the distance around. And then you multiply by L. This is the area of the side. So if that's the area of the side, then that's what the result of integrating up the area of the side is. And so this is times 2 pi r times L, like this. And so that's the flux. And by Gauss's law, the flux is the charge enclosed over epsilon naught. So lambda L over epsilon naught equals E magnitude at r times 2 pi r times L. And so what we conclude from this is that the electric field has a magnitude at r equal to, so check this out, the L's cancel. And let me comment on L canceling in just a second, but look at where everything goes. So the epsilon naught stays downstairs. There's a 2 pi that comes down with it. So there's 2 pi. There's an r, and then lambda on top. So I think that's everything. So 2 pi r, epsilon naught already there, lambda's left, and the L's cancel. So the L's cancel. And the answer is heck yeah, it shouldn't be there. And the reason was, right here, this is why L cancels. L cancels because there is no dependence on anything particular in the z direction, and L is a z direction detail. But because of the symmetry, it's really the infinite length of the line. So when things are infinite, the idea of an origin disappears. Because it didn't matter where you put the origin. If I put it here, I've still got an infinite amount of charge above and an infinite amount of charge below. And the charge distributions above and below this new origin are identical, right? Because of the uniformity. So the uniformity along the z-axis of the charge distribution is the symmetry, and that symmetry dictates the fact that the electric field can't depend on any detail from the z direction. So the detail from the z direction that was left over for Gauss's law was capital L, but Gauss's law, because we're making arguments by symmetry, Gauss's law will never keep a detail as a result that symmetry told you wasn't important, is the idea. So this video has become very long, and there was another topic that I wanted to describe called the shell of charge, and I wanted to explore the shell of charge with Gauss's law. But what I'm going to do is put it in lecture 11. Yeah, so I'm going to do that because I think this video is already like an hour long.